Well, hello. Hello, I'm Jason Gibson, CCO at IACMI. Innovation Insights is our monthly webinar series highlighting the people, the ideas, and partnerships driving advances in composites and manufacturing across the U.S. As part of the Manufacturing USA network, IACMI leads national efforts to scale new materials, develop sustainable processes, and strengthen U.S. manufacturing competitiveness. But before we get started, I'd like to mention that if you have any questions during our presentation, please enter them into the Q&A section, and we'll be sure to ask them to our presenters at the end of each section. At ACME, our mission is to convene, connect, and catalyze. We convene the composites community to share ideas and opportunities. We connect industry, academia, and national labs, and catalyze real progress through collaboration and commercialization. Today's Innovation Insights reflects that mission, highlighting new ideas, technologies, and applications driving the future of composites. For those new to IACME, we accelerate composite innovation to strengthen U.S. manufacturing and workforce competitiveness through co-funded projects, access to world-class facilities, and a powerful national network. If you're listening today and you're not currently an IACME member, we want to encourage you to consider the value of joining. When you become an IACME member, you gain more than affiliation. You join a national network accelerating innovation in composites. IACME gives you a platform to engage, contribute, and make an impact. We'd be excited to welcome you into our community, so please visit our website and reach out to us by filling out the online form. Now, one upcoming event I'd like to highlight as we get closer is our 2026 members meeting. It's taking place in Denver, Colorado. Now, this is a members-only event at no cost, and it's one of our best opportunities all year to connect across the IACME network. You'll be able to network with nearly 200 member organizations, hear updates on our latest research and working group activities, and share what your company is working toward in the composite space. It's a great forum for aligning efforts, sparking new collaborations, and making sure your priorities are part of the broader conversation. Now, I am excited to announce that we're celebrating the 50th episode of Innovation Insights. Innovation Insights began during the uncertainty of COVID, created as a way to keep our community connected, informed, and moving forward. What started as a response to disruption has grown into a valued platform our audience continues to engage with and appreciate. Reaching our 50th episode is a testament to the sustained interest and the consistency of this series. Now, while I've had the opportunity to host only a handful of sessions, the real credit belongs to the team behind the scenes, especially Kim Hooden for her tireless coordination in the background, and Dale Brojas, who guided this series for many years prior to his retirement. We're grateful you've joined us today and are excited to celebrate this milestone together. Welcome to our 50th episode of Innovation Insights. Now, if this is your first time attending, we encourage you to explore past episodes that are available on our website. Since its launch, Innovation Insights has convened members and partners from across the composites ecosystem to share practical applications, emerging technologies, and lessons learned from active R&D and commercialization efforts. This series is designed to keep you current on industry trends while creating direct access to the people and ideas shaping the next generation of composite materials and manufacturing technologies. And today is a good example of that. So let me introduce our speakers. Today's Innovation Insights brings together presenters who are each advancing composites from a distinctly modern, industrialized perspective. Their sessions explore how digital material design, scalable recycled carbon fiber solutions, and high-volume processing technologies are reshaping the way composite materials are developed. We'll begin with Dr. Leyla Mirmomen, CEO and founder of Optimuos, who will introduce MetaXlab. It's an end-to-end AI-driven digital platform designed to accelerate composite material design and qualification. Her session will highlight how digital lab environments and material digital twins can predict performance, manufacturability, and reliability under mission-relevant conditions, helping organizations reduce development cycles while improving confidence in advanced material systems. Then next, Jeff Hall, Director of Client Relations at Carbon Fiber Recycling, will provide an update on the company's scalability and technology enhancements aimed at expanding efficiency in recycling carbon fiber. His presentation will examine emerging product developments, including standard agglomerated fiber for infrastructure applications, newly introduced milled fiber solutions, and progress on pelletized carbon fiber products engineered to improve flowability. And then finally, we'll close with Dario Pigliafreddo and Shane Brody of Canon, who'll present their composite processing solutions for high volume applications. Their session will explore patented technologies such as the dynamic overpacking system for high pressure RTM and the triple vacuum frame for compression molding. So with that, I'd like to get us started. Let me turn it over to Dr. Leyla Mirmomen. Leyla?
Thank you, Jason, for amazing introduction, and thank you, IACME, and the audience here for giving me the opportunity to introduce MetaXlab, which is, as Jason mentioned, is a digital platform for material characterization and development. Let me just go in a full presentation. Like any other entrepreneur, I would like to start with talking about the problem that we are solving. In any material and part manufacturing industry, including composite manufacturing industry, an inseparable part of the process is testing, characterization, and performance evaluation. Whether we are developing a new formulation or design or producing an existing one, or optimizing our manufacturing process, we require to test and validate the material and the part that is being manufactured to make sure it is is built against the standard and the targeted performance. And this translates into iterative sample preparation and lab work and analysis and characterization, which all of us know that is very much labor intensive and heavily manual, and consider a bottleneck for new development or advancement of the existing one. The platform that we are developing and we're building.
Layla, sorry to
Yes.
interrupt, but we don't see any of your slides. Did you want to share your screen?
I am sharing my screen. Oh,
You have more than one screen. Sometimes that's the issue.
yeah, that's the problem. Thank you for pointing that out. Okay. Do you see my screen all right now?
We do. We just see the whole thing. If you put it in presentation mode, we'll see just there we go. Looks good.
Perfect.
Yes,
Thank
Thanks.
okay.
you.
Sorry, my computer has like so many things running, even though I closed most of them, but this make it a little slow. Um, yeah, the platform that we are developing is aiming to enable the industry user to digitally predict the property and also evaluate the performance of the material. In addition to that, is enabling them to develop new formulation or even optimize the manufacturing process and see and analyze the output before heavily investing in the physical process. We estimate that this platform is able to remove 70% of the manual work that's currently being done and expedite the whole process, and it can easily become part of the workflow, the current workflow that is going on in the manufacturing process. The architecture of the platform is modular, and what that means is that we don't have a generalized model. We have individual modules developed for each material family and each test using advanced computational techniques. But the good news is that the user, they don't really need to have any skill in simulation and modeling, as is modules designed in a way that work automatically and provide the outcome that is required. And the users only need to communicate with these modules through a very simple UI, which I show it to you in the next slide. Currently, we are in the TRL5 of development with the focus on reinforced composite and self-healing composite and mechanical property lab. And all the modules that have been developed have been validated against experimental data. I would like to stop talking abstract and actually show you a short video demo of how the tool works and give you a better idea of what I'm talking about.
Material development and characterization are slow, expensive, and unpredictable. MetaXlab changes that. In this short demo, you'll see how our intelligent platform builds a digital twin of the material, by predicting its microstructure and properties, simulating its performance, and generating complete engineering reports instantly and automatically. This demo focuses on particle reinforced thermoset composites, including rigid particles and chopped fibers with aspect ratios under 5. With that material system defined, the workflow begins with material definition, where the basic identity of the composite is established. From this point forward, MetaXlab's multi-layer computational engine, built on the physics and chemistry of Cure kinetics, network formation, and polymer behavior, configures the workflow automatically. The next step defines the reinforced phase. Here, the user selects the reinforcement type and inputs properties such as geometry, stiffness, and volume fraction. Based on these inputs, the platform activates morphology-dependent formulations, reinforcement matrix interaction models, and dispersion and packing rules that determine microstructural behavior. Next, the polymer matrix chemistry is selected. This single input triggers the physics engine responsible for Cure kinetics, viscosity evolution, modulus development, and chemistry-dependent constitutive behavior. User input is intentionally minimal. You provide the chemistry, and MetaXlab manages the full multi-layer physics. Manufacturing and curing parameters are then defined. The platform uses this information to update material behavior throughout the curing process, continuously evolving modulus, interactions, and microstructure as the polymer transitions from uncured to fully cured. MetaXlab then constructs a high-fidelity digital twin of the material. Here, the user selects the intrinsic properties and microstructural features to include. The resulting digital twin represents the final microstructure, intrinsic matrix properties, and composite properties at full conversion, and can also capture how these properties evolve throughout processing. The digital twin proceeds to digital characterization, which functions as a virtual testing laboratory. Each test is a digital reconstruction of the corresponding ASTM standard. Users can perform tensile, flexural, compression, shear, fatigue, or fracture tests and define loading rate, environment, temperature, and nonlinear options. MetaXlab automatically applies the appropriate boundary conditions and loading profiles, runs the digital test, and outputs performance metrics. Here, the user runs the full simulation and can generate 2 reports. The first is the morphology report. It visualizes the simulated microstructure and quantifies particle dispersion, clustering, nearest neighbor distances, and aggregation behavior, providing a technical fingerprint of the composite morphology. The second is the full digital twin report. This combines microstructure information with intrinsic material properties and performance metrics, including flexural modulus, strength, maximum deflection, and the complete load deflection curve. All algorithms and outputs shown here have been validated against experimental datasets for this material family. Accuracy and tolerance ranges are updated continuously as new data are incorporated. MetaXlab delivers a physics-grounded, autonomous workflow with minimal user input, enabling faster development cycles, reduced cost, and deeper insight into material behavior. Upcoming modules include a formulation design station, where target properties define the required formulation, and additional tests such as fracture toughness, further expanding the platform's capabilities. Material development and...
I'm sorry. Before I stop my talk, I just want to say that what we are looking for at this point of our development, and I hope that people who are listening find alignment with us. We are looking for a pilot partner to apply the framework that have been developed with the new family of composite material and give the access of using the capability of platform that we have to our partner, and also developing modules which is specifically designed for their family of material. Also, we are looking for early adapters in companies or people who are working with particle chopped fiber reinforced composite to give access to use the advantage of the tool that have been developed and module that have been developed to give us their insight and provide us the insight so we can use it for further advancement of the module that have been developed. I am going to stop now and just leave the open for people if they have any questions.
Yeah, that's great, Leyla. I appreciate all this. You mentioned in there about how you can have the digital twin and create ASTM testing results based on that digital twin. And you mentioned that you do have some correlation with experimental data. Can you elaborate on how accurate it is compared to true physical properties that you've gained from ASTM testing?
So all the models that have been developed have been validated against experimental data, either provided in literature or have been done by our partners. They have done experimental data and provide the result of experimental data. We ran the simulation and the models that have been developed for the same type of material that they test. Also, we have done blind tests and make sure that the model are accurately able to predict the properties based on different testing conditions for different material within the family that we worked.
Great. And it sounds like you're expanding now into more SMC, BMC type applications for chop fiber reinforcement in there. What are some, you mentioned you'd like to have some pilot partners and early adopters. Like who would be the best candidates for you that you'd love to see sign up with you and just work with you on developing the next stage?
Yeah, in terms of early adopters, anyone who is working in the area of particle reinforced composite or chopped fiber reinforced composite, that would be great to just reach out to me and we let them use the modules to give us their input and insight, and it would be further validation what we are doing. And for pilot partner, we are looking to expand. So if in any area of reinforced composite, people have interest in using the capabilities that they already developed, that would be great that we start a pilot project. What we do in pilot project, we are building a digital twin of material module for that specific family of material and validate that against their data and then let them interface with the digital lab and get the output to see how that works, and they're free to validate the data that they're getting with the experimental data they already have, and that would give them like a early access to all the modules that have been developed and having their own modules for their specific material. So
Great. So if you're out there and you're listening, feel free to reach out to Layla if you'd like to connect with her. I don't see your contact information up on the
yeah,
screen.
that
If you
was the
wouldn't mind.
last slide. Here
There
we
we
go.
go.
Yeah.
So you can see her emails there. Feel free to reach out to her directly. She'd love to have some engagement there to move on to the next stage. Well, Dr. Layla, I appreciate your presentation. Let's go ahead and turn it over to Jeff Hall. Jeff, if you wouldn't mind sharing your screen, and let's go ahead and jump into your presentation.
All right. Thanks a lot. Give me just a minute. All right. Bear with me. All right. Do you got the notes page this time, Jason?
We got the notes page, so you'll need to
All
swap
right.
it real
Let's
quick.
swap it again here.
There you go. Looks good.
Perfect.
All
Thanks,
right.
Jeff.
Great. Thanks, guys. Well, first of all, thanks for inviting me. Yeah, oh, I'm getting a little bit of feedback here, but hey, so thanks for inviting me. Um, Also, congratulations to the IACMI team for your 50th Innovative Insight. I'm glad to be a part of it here. So my name is Jeff Hall. I'm the Director of Client Relations at Carbon Fiber Recycling. We're located in Tazewell, Tennessee. I think most of you, or at least some of you, probably know who we are. For those of you that don't, I've got a brief introduction I'm going to walk you through here. So at our facility here in Tennessee, we operate a large-scale continuous feed pyrolytic reactor. Basically, what that means is we use pyrolysis to liberate the carbon fiber. And as long as we're putting material into one end of the system, we've got clean recycled carbon fiber coming out of the opposite end. So here are some of the things our clients tell us make us unique. Give me just a second here while I try to navigate over to my notes page. But so first of all, it's the quality, right? The RCF we produce is consistent and clean with virgin-like attributes. We've done quite a bit of testing, and those are the results that we've been able to find. Secondly, is we're feedstock agnostic, and what that means is CFR is capable of recycling materials that go above and beyond just in post-industrial waste. So because we recycle not only dry fiber, but cured composites and pre-preg materials, this allows us to move into post-consumer waste as well, right? And the people that recycle with us absolutely appreciate that because it allows us to recycle the bulk of their material, not just the dry fiber materials. That kind of leads to the supply chain side of things. So what we offer is supply chain stability. So since we have access to large amounts of domestic feedstock materials, the RCF we produce is not tied to global economic pressures. I think anybody that works with carbon fiber understands that that can be a little bit of a challenge, especially, faced with some of the things we're faced with right now. And then lastly is just the scale, the sheer scale at which we operate. So at our current location, we can produce north of 3 million pounds of RCF. That's 3 million pounds of material that we can recycle or more, right? But we can also produce over 3 million pounds of clean RCF that can be commercialized and then, utilized for other applications. So we'll kind of move over and jump into the product side of the fence. And this is where it might get tricky. Bear with me while I try to change tabs. Did that change for you guys? Okay.
Yep.
Yeah, it
looks
like
good.
it did. Okay, great. Thank you. So as you guys know, developing recycling solutions is a two-sided coin, right? So on one side, you've got the recycling aspect, but on the other side is the commercialization of the raw material or the material that you're getting out of the recycling piece. And you need both sides to be successful. So CFR, we've worked to create formats for our RCF to simplify the commercialization process, right? So first of all, what you're seeing at the top of the screen is our base product that we offer. We refer to this as our agglomerated RCF. This material is comprised of liberated fiber from various feedstock supplies. For example, high pressure vessels, hydrogen, compressed natural gas tanks, race cars, aerospace, cured composites, a lot of the stuff that gets recycled. So as far as the attributes of that material goes, it maintains the attributes of the original base material. Because we have several different brands that we recycle, if you were to take a look at our technical data sheet, you would see that, for example, tensile or tensile strength, if you look up here in attributes, you'll see that we offer that in a range. So when we're preparing our specifications, we have to look back at what the base material was that we were recycling. So our agglomerated material can be used as is for applications like, for example, infrastructure applications like fiber reinforcement for concrete and asphalt. And we also use this material as the base material or the base product that we create other materials out of. And for example, if you look at the bottom of the page here, you're going to see our milled RCF. So this milled RCF has all the same attributes as the agglomerated RCF, but it can be milled to various aspect ratios. And one thing that makes it unique is the fact that it has no sizing on it, which gives it fantastic EMI and RF shielding capabilities. And we've been doing some work with Sandia National Lab that kind of reinforces that statement. And we've got some technical data that would be happy to provide to anybody that would like to learn a little bit more about some of those results for EMI and RF shielding. So both of these products you see here on the page are available and sellable, released at production scale today. Let's see, moving on. Yeah, one other thing we're excited, you may have seen some of this in the news, so to speak, is our relationship with James Cropper. So James Cropper has been able to take our recycled carbon fiber and utilize it for veiled, excuse me just one second, utilize it for non-woven veil applications. So I'll let the James Cropper kind of speak to all the attributes and wonderful things about their non-woven veil, but I will share with you some of the applications here. aerospace interiors, advanced air mobility, automotive panels, and sporting goods. James Cropper has also got a new product that has they have their standard non-woven product, but they've also been able to align the fibers to create semi-structural properties, which is also pretty exciting. So if you'd like to learn a bit more about what James Cropper is doing, I've got a link to their website here. And I'd also be happy to make an introduction. If anybody wants to reach out to me, I can introduce you to the people that we're working with over there to answer some of your questions. And then lastly, from a product development perspective, we're also very excited to talk about our pelletized RCF. So what we've done is we have gone in and taken our standard agglomerated fiber, and we have, give me 1 second here, my apologies. So we've taken our standard agglomerated fiber and we've pelletized it primarily for the purpose of increasing the bulk density of the material. So we engineered this material, this pelletized carbon fiber specifically for compounding, right? So if you've ever tried to compound with short chop lengths of virgin carbon fiber, you'll find that the bulk density is so low that it can cause flowability issues. So by going in and increasing the bulk density of the material, we've taken that challenge away. Some other features of this material is there's various fiber lengths within this pellet that you're looking at, some as long as 8 millimeters that we've measured. And by having the various fiber lengths within the pellet, you're able to attribute certain attributes that you would get from the various carbon fiber lengths within the compound that you're making or the polymer that you're working with. We also apply sizing to these pellets. So what you're looking at, this image of this pellet, there's no binder material there. Outside of the sizing, there's no polymer holding that pellet together. It's essentially pure RCF with the addition of around 1.5% sizing, which makes this pellet compatible with a very large array of different types of polymers. So of course, as we mentioned before, this material is all 100% sustainable, and you also get that supply chain stability benefit, from utilizing RCF as a carbon fiber reinforcement in a polymer. So in summary, start off with the LCI, right? So we've performed some internal life cycle analysis, and we feel we have one of the best, lowest LCIs for carbon fiber products in the industry. We actually metered some equipment, natural gas usage, electricity usage, and we took a look at what we were doing. And ultimately, our goal is to drive into a carbon negative situation. So we also continue to invest and improve in our efficiencies. If you look at this image here on the lower right, you'll see a recent shredder processing upgrade that we're going through. And just to put it into perspective, to kind of scale it for you, you can see the lull sitting behind the primary line. And if you look back here to the left, you can see Mike standing next to one of 4 electric motors that drives our secondary shredder system. So we also talked about earlier about being feedstock agnostic. This supplies us with a really, really good supply chain stability. Not only if you're looking for somebody that you're going to recycle with, right? They can take a broad array of your materials, but because we have the amount of production volume that we have today, we can support industries that may have a large need for large volume before they can adopt it and utilize that material across an array of their products. We offer cost-efficient closed-loop solution. And I guess at the end of the day, we're pretty excited about where we're headed. And I think from an efficiency perspective and just driving the LCI down, I think we're doing a lot to kind of move the needle towards actually providing a viable, sustainable solution for recycled carbon fiber. And I guess with that, I'll just turn it over to you, Jason, see if anybody has any questions. Thank you, guys.
Yeah, thank you, Jeff. And we do have some questions. So let me start with the first one. How does the pelletized recycled carbon fiber material compare in mechanical properties in a polymer compound compared to non-pelletized recycled carbon fiber?
That is a fantastic question. So I told you the reasons why we designed it, right? And we know that typically when you compound with carbon fiber, say for example on a twin screw, that fiber is broken down to less than 300 microns, around 300, sometimes less. So we kept that in mind when we were engineering this pellet. And what we're doing right now is we're working with the Polymer Center in Charlotte to do some lab analysis to kind of look at those characteristics. So that information is kind of forthcoming. I would say just stay tuned. But our intent is to develop kind of some best practices for processing the material and a technical data sheet along with some like real world empirical data that you can look at to check those performance characteristics.
Great. Next question. What are the fiber lengths in the agglomerated recycled fiber?
So we refer to that material as our 15 millimeter. It typically, you know, as you can probably seen from the picture, right? But it's a variation. So if you look at the bell curve right now, that material lands at nominally around 15 millimeters. Because we are doing some upgrades, it'll change the amount of fines available in it. So we don't have like a fiber dispersion chart to provide, but it is something we'll be developing pretty shortly. Nominally, I would say it's about 15 millimeters.
Okay. And then do you have any plans to recycle materials other than carbon fiber?
Not currently today. We get asked that a lot. We get a lot of air-emitting glass, and glass is a contaminant for us, right? It's a mineral that stays behind when, you know, so we don't, it's tough for us to bring in, you know, products that maybe have a layer of fiberglass on the outside of them and things like that. But we do get asked that question, but for the time being, we really worked hard to kind of perfect this carbon fiber recycling technology. And right now that's where our focus is at.
Understood. Well, it's exciting times. Glad to see how you've accelerated there and appreciate your presentation.
Yep, great. Thank you.
So go ahead and stop sharing your screen and let's go ahead and turn it over to Dario and Shane. Dario and Shane, if you wouldn't mind sharing your presentation. It looks good, but don't hear you yet.
Oh, okay.
Shane
I was
is
just
available.
making sure it was up. All right. Hello, everyone. Thank you for attending this presentation, and a special thanks to IACMI for allowing us to show you some of our technology. My name is Shane Brody. I'm a technical sales engineer from Canon USA in Pittsburgh, Pennsylvania. I'm joined by my colleague Dario Pigliafredo from our Italian headquarters. Just to give you a background, the Canon Group was founded in 1965, privately owned then and now. The company originally specialized in reactive polymer equipment. Over the years, we've added numerous technologies to our group, as you can see on the screen. But most applicable, since the 1980s, we've made significant strides in composite processing technologies. The Canon umbrella is far-reaching across the globe. We have numerous branches, some specialized within Europe, the Americas, the Middle East, and Asia. Now I'll start with our equipment. The first one being, aside from this, we have our bread and butter, the high-pressure dosing machines and high-pressure mix heads. These systems can be applied to many processes, including HPRTM or high-pressure resin transfer molding. For chemicals, including but not limited to epoxies, polyurethanes, DCPD systems, and many others. Actually, a version of this machine will be used at IACMI's SURF facility or scale-up research facility in Detroit for HPRTM prototyping using DCPD chemistry. The mixing head applies to, like I said before, HPRTM. The process this process in which a dry preformed material is put inside of a mold cavity. A press clamps the material in place and adds pressure resistance within the mold. Then a dosing system, like previously mentioned, is connected to it and will inject a 2 to 3, maybe more component resin system inside of the cavity. The high pressure that I mentioned before is built within the metering system, then translated to the mold and final part. But the pressure is translated into the final part through the resistance of the part and the material or the chemical materials passing into the mold. Just one thing to note. After a few minutes after pouring, the material within the part can be cured and removed, and this is a lot different from the several hour process for standard methods. In addition to this, we have the ability to produce tooling for aerospace and composite applications and other applications. In addition to the metering system and tooling, we can supply additional ancillary systems to complement the process. One example would be the dynamic overpacking system that we'll talk about a little bit later. Along with our metering equipment, we manufacture high tonnage presses with very good characteristics that allow us to be more effective in the composite market. For example, our parallelism control built into the press system is one aspect that adds a lot of accuracy and repeatability to the process. And repeatability is very, very important, especially in aerospace, where precision could mean life or death or significant cost and loss of material and time. Through automation, we can attain a higher degree of accuracy and repeatability in the process and final products. And with that in mind, we can supply complete turnkey lines, turnkey systems for a multitude of processes, products, and compounds, some of which include HBRTM, like we mentioned before, wet compression molding, sheet molding compound, pre-preg compression molding, glass fiber reinforced molding, and many others. We also have a dedicated R&D team and a full furnished lab, including customized molds and tooling to fit your product, where we can trial most chemicals, processes, and applications. Now I will hand it off to my colleague, Dario. Dario, take it away.
Thank you, Shane. Thank you very much to everyone for the opportunity to present a couple of interesting technologies that we developed here in Canno in the last few years. The first one is the TVF. TVF is the acronym for triple vacuum frame, which is more or less what you see in this picture. It is basically a metallic frame on which we apply on the top side and on the lower side two thermoplastic films that are kept stretched thanks to the vacuum applied to the frame, and then that we will heat up in order to form at our necessity. We also apply vacuum in between the two thermoplastic films in order to then maintain components inside of them. This is an example of this frame, some pictures of it. In between the thermoplastic films, we can place, for example, a pre-preg material, and we can use this frame to transfer it in an automatic plant from the beginning to the end of the process. What are the advantages of this TVF? First of all, as anticipated, is fully automatable, so it means that we can integrate it into a line and move and transfer the pre-preg material from the beginning to the end. It has a lot of preforming capability thanks to the stretchability of the material and thanks to the vacuum that we have between the two layers of thermoplastic film. We can remove air from the pre-preg material itself. It is a clean equipment because being the pre-preg, the tackiness of the pre-preg contained within the two films, we are able to avoid dirtying grippers, for example, of transfer needles and stuff like this. And of course, this means that we can avoid also release agent when we have, for example, a preforming tooling. It is also very safe for handling complex geometries and complex stacks of material, for example, because we are avoiding misplacing the components, for example, cores or sandwich structure, and we maintain the orientation of the fiber correctly as an aeronautic process should do. In some cases, we are also able to skip somehow the preforming phase and move directly the material, the prepared material, to the pressing stage. These are some images to better understand how it works. From the left, we have a compact oven, which is heating up the material and the thermoplastic film. We have a transferring phase in which we are bringing the material under a preforming press, where we will have a tool. We will have the preforming phase under the tool, and then simply we demold and we move the grippers back to the first phase, and then the film within it is contained the material in a second stage, when the film is going to protect the material, and you can just peel it off manually when we have to use the prepreg preform for the second stage. Let's now discuss about the second technology, which is quite interesting for aerospace application, which is the DOS, or Dynamic Overpacking System, which is a device which is able to control cavity pressure. Transfer this concept to HPRTM. On the left, you see the direct diffusion system. On the right, you see the Dynamic Overpacking System, which is basically an accumulation device which is able to re-emit mixed resin at a defined flow rate inside the cavity of our mold. The flow rate is defined by something that we set in terms of in-mold pressure, which now can be whatever we want, not just limited to 1 bar, but we can arrive, for example, to 100 typical HPRTM pressures. The main characteristics of this device are that it's position control during the accumulation phase, but pressure control while we are injecting the material inside the cavity, in close loop with the pressure that we have inside our laminate, for example. The volume is around 360 cc, but can be changed. And it is controlled in temperature, which means that we can keep it cold while we are gathering resin, and we can heat it up when we have to cure it at the end of the process. In terms of flow rate, we can arrive from a few cc per second down to few cc per minute, which is very important to finally control the process in terms of pressure. And it is completely self-cleaning, which means that we don't have to use solvent or any kind of other consumable materials to operate it. This is the 3D model of a real mold that we made for a customer. You see on the top here, this is the injection mixing head, which is going to deliver the material to the mold. These two here are the two dynamic overpacking cylinders, let's say, which are going to pressurize the cavity inside the mold. In this case, the mold contains 8 cavities, which are all kept pressurized by these 2D. Now, to better understand what happens during an actual injection, I'm showing here an example of a pressure profile in a real component. At the beginning, you will have the start of injection opening the mixing head and a slight increase in pressure because, again, as Shane said, the reinforcement is resisting the flow of material. At a certain point, you will have a peak of pressure because there will be no space to go for the material left. In this case, in a normal HPRTM process, you will close the mixing head, but in the DOS application mode, you open the DOS, the pressure will decrease, and you keep injecting. At a certain point, also the space for the DOS in the DOS will finish, and you will have a second pressure peak in this position. You close the injection head, and then you let again the dynamic overpacking system do the work, and it will maintain the pressure at a value that we define, in this case, for example, 40 to 50 bars. This is an example of a component made with and without DOS. Of course, typical HPRTM parts look much better than the one here on the left, but in this case, we were using a high TG and high shrinkage resin rated for aerospace application. So in some cases, the DOS is crucial even without the need for fragile inserts management. To summarize what we said until now, we are able to combine the advantages of both HPRTM and vacuum RTM because our target is to actively control the pressure inside the mold by changing the flow rate. Our target is to be able to manage fragile inserts. We want to avoid fiber washout, and we want to compensate for chemical shrinkage after the injection is finished. Then we reach, of course, as an objective, less void contents. We have better mechanical properties. We arrive to 60 to 65% of fiber volume fraction, which for HPRTM is a lot. And we also have better aesthetical properties, as you have seen before. This is it. Thank you very much for listening to us. These are our contacts. And if you have any questions, we are available for you.
Well, thank you, Dario and Shane. I have a few questions for you. I'm really impressed with the overpressure system. You talk about how you get lower void content with it, obviously better aesthetic properties because of the shrinkage aspect. Would you say are you approaching the same type of physical properties you get with a pre-preg material in an autoclave that's processed under pressure? Or is it still shy of what you can get with a pre-preg in an autoclave?
I think we are slightly shy of this, but we have seen, for example, TC scans of our components made in an aerospace and aeronautic setup, and is very, very good. So probably working a little bit more on this, we will be able maybe to reach something close to a pre-preg mechanical characteristics, let's say.
And then have you tested with all different types of resins, epoxies, urethanes, and the DCPDs, or?
Yes, we did. Let's say that the main advantages are where we have high shrinkage rates. So it really depends on the chemical system. In some cases, it's not necessary to use the DOS. In some cases, it's absolutely necessary. We have seen a lot in epoxy. Something could be for the DCPD as well, and polyurethane in some cases as well.
Okay.
But whatever we put inside, more or less, is the same. Then the effect is different.
And let me back up on your presentation. You had, I think you call it the three-frame system, where you hold the thermoplastic in between the thermoplastic films. I'm assuming those thermoplastic films that are holding it together are part of the finished part after you've compressed. Is that true?
Yes, they remain with the finished part, and they protect it if we need, for example, to transfer it. We have customers, for example, which are selling preforms, and this is a good way to maintain it in a certain way. But let's say that it's very easy to manually demold it, or we have also solutions that automatically do that, and we are able to transfer it even without the film outside. So depending on the kind of film, it can remain with the part or be taken out.
So, and then I'm assuming that if you're processing LMPAEK, the film needs to be LMPAEK. If you're processing PPS, the film needs to be PPS. Is that a safe assumption?
No, the kind of material, it really depends on the kind of, let's say, of the process, the temperature of the process, and so on. Also, the thickness of the material. Typically, we have our lab and we test something with our customer beforehand in order then to define the kind of film we want to use.
Great. Well, I appreciate your presentation. A lot of good technology there. It's pretty exciting. Hopefully our members can gain something from that. So let me go ahead and share my screen again. So as we close out, I just want to remind everybody of our future innovation insights that are coming up. Our next one is Monday, April 13th. We've designed that one to be focused on nuclear applications. So we're going to have 3 key presenters, all geared around nuclear applications. Would love to see everyone there. Please mark your calendars for everything we've got there. Appreciate everyone's time today. Feel free to reach out to me directly if you have any questions and you didn't catch all the contact information for the different presenters. We will be sending out the presentations in the next few days to everyone that registered. And if you have future questions that you didn't get a chance to ask, feel free to send them to us and we'll ask them to the panelists behind the scenes. So thank you again for your time. Appreciate it. Everybody have a great day.
Thanks, guys.
Thank you.
Thank you.
Thank you very much.